Dynamic equilibrium. So equilibrium is our next topic of discussion, and it's called a dynamic equilibrium because it's a situation where two opposing changes are occurring at the same time at equal rates and their effects cancel. It's dynamic because it's constantly happening. As a result, you can no longer see any changes in the reaction, so it'll look like the reaction has stopped. The observable or macroscopic, so macroscopes are your eyeballs. So the observable properties like color, pressure, concentration, pH are all at constant. It looks like nothing is changing. You must have a closed system for equilibrium to establish, and the temperature must be constant. We're going to look at three different types of equilibrium. So the first one is solubility equilibrium. And basically, solute, the stuff that's being dissolved, the solids are dissolving while their molecules, if they're covalent, and their ions, if they're ionic, are precipitating or crystallizing out of solution. So what happens is you have the calcium, let's say for instance this example, you've got your calcium fluoride solid dissolving into the ions, but at the same time, at the same rate, so the same speed, the reverse is happening. Calcium fluoride ions are coming together to precipitate out. So this is called solubility equilibrium because it has to do with the dissolving solids. And the forward rate is equal to the reverse rate. So when we write equilibrium equations, we now, instead of using a single arrow, we use a double arrow to indicate that the reaction is going in the forward direction. So forward is written as left to right, normal, for us that are new to equilibrium, and then the reverse reaction will be going back from the products to the reactants. So reactants to products is considered to be forward, and products to reactants, as it's written, is considered to be reverse. We don't talk a lot about phase equilibrium, but it's really important. It's basically when two states or phases are occurring at the same time and at the same rate. You have to have a closed system. For example, water can be in a jar, but it has to have a lid on it. So no matter or energy can escape. So basically, we're going to look at liquid water, and it will evaporate. And you'll see in a water bottle that you've opened, or a pop bottle that you've opened, or in maybe a reusable water bottle, you'll notice that there's condensation above the liquid on the walls of your container. And that is because liquid water has evaporated out, and when they collide with the surface of your container, they will return to their liquid state. So they go from liquid to vapor to gas state, and then back to liquid. And this is going to happen at the same rate. The evaporation happens at the same rate as the condensation in this reaction. But if you change the temperature, if you turn up the heat, you disturb this equilibrium. It's no longer occurring at the same rate. And then what will happen is it'll change, and then it'll appear to stop again when it reaches a new equilibrium. So for this example, we would have the double arrow again, because we have liquid water changing to vapor, water vapor, the gas state, and then the water vapor is condensing into the liquid state. We'll end up talking mostly about chemical reaction equilibrium. So basically, I mentioned that it looks like the reaction stops. So this is actually a graph of what happens to the concentration over time. So you can see that for this reaction, we've got hydrogen gas and nitrogen gas reacting to produce ammonia. So at time 0, we don't have any ammonia. But as the reaction proceeds, it will start to increase, but then it stops. It seems to stay at the same concentration. It's not going up or down. It literally is like it's stopping. Because hydrogen and nitrogen are being used up initially, their concentrations will decline, and they flatten out at the same point. So when you see a graph of data, you know equilibrium has been reached when the graphs flatten out. There's no actual change to the concentration at that point. It's reached equilibrium. And that's because the rates of the forward reaction and the rate of the reverse reaction is equal. Now, this is a very important and well-known process in the chemical industry. It's done at very high pressures and several hundred degrees Celsius in a closed container. But the reaction does not consume all of the hydrogen-nitrogen gas. So we get this stopping of the reaction where it flatlines. So we're going to look soon at how we can manipulate the system so that we do use up all of our reactants and produce the maximum amount of ammonia possible. But that's a lesson for another day. So basically, we can write this reaction as hydrogen gas plus nitrogen gas, and then a double arrow, and then ammonia. So as ammonia is being formed, it's actually breaking down and forming its reactants. Now, it doesn't matter which direction we approach equilibrium. So that means if I have a container of hydrogen and nitrogen gas, I will form ammonia, and then eventually it will stop. The reaction will stop changing. So the concentrations of all three chemicals will be constant. I can also put ammonia into a container, and it will start to decompose into hydrogen and nitrogen gas. So the opposite happens. And what happens is eventually it will stop, and I will have again ammonia, hydrogen, and nitrogen that seem to be at constant concentration. So you can approach equilibrium from either direction, and at that specific temperature, it will be the same. You get the same values. So almost all chemical reactions reach a state of dynamic equilibrium. However, that equilibrium may be difficult to detect because of the amount of products or reactants. At equilibrium, it's virtually zero. So we have three types of reactions we're going to be writing. We've got a quantitative reaction, which pretty much says this goes to completion. So it's majority, more than 99% of your chemicals is your product. So that is considered to be a quantitative reaction. So we always write it with a single arrow rather than the big and little equilibrium arrows. So we write it like this with just a single arrow. This happens with strong acids. The acid is 100% ionized. Its reaction goes to completion. Then you've got an example where there's basically no reaction. There's a lot less than 1% of any products formed. So water vapor doesn't decompose into doesn't decompose into hydrogen and oxygen gas, which is good, because on a hot, humid day, we would not want the air to be highly combustible. So basically, water vapor is extremely stable at room temperature. So the reverse reaction is favored. It won't go to the right. So then we say, if that happens, that you really don't form any products that you can measure, then it's an NR, it's a no reaction. And thankfully, here on planet Earth, water vapor does not decompose into hydrogen and oxygen gas readily. And then, of course, the third type of reaction we're going to look at is this new idea of equilibrium, where you've got a reaction that goes partially to products, partially to reactants. And we'll talk about where the equilibrium point lies based on, does it favor products or favor reactants. There are 4 conditions that apply to all equilibrium systems. So these are rules. So equilibrium is achieved when the rate of your forward reaction equals the rate of your reverse reaction. And that's when we write it as a double arrow. So if a chemical reaction can be reversible, we will start putting in the double arrows. Observable properties of the system at equilibrium are constant. You don't see a change in color, you don't see a change in pressure or concentration or pH. It's like the reaction has stopped. It hasn't. It's just the rates are happening at the same time. Equilibrium can only be reached in a closed system, so there's no in or out. Therefore, the system is always at constant temperature. So a lot of reactions, a lot of questions will state at this temperature, and that's only for the K value. It's not anything you need to use in your calculations. It's just a statement of fact. Equilibrium can be approached from either direction. So you can either start with your product in a container, or you can start with your reactants in a container, and eventually you will have all 3 or all 4 substances present. And once equilibrium has been reached, the reaction appears to stop.